Hey guys, what's up? Welcome back. Today, equations of lines and planes continued. We got an exam probably coming up next week, I think. I'm trying to think of what the date is. So it should be coming up pretty soon. I think it's like the 24th actually, is Wednesday. That's tentative for now. We'll finish up 12.5 today. And we'll get into 10.5 Wednesday, 12.6 Friday, 10.3 Monday. Wednesday may be a little quick. We'll see. I know I've been talking to the other teachers this summer in some of the classes that you guys are taking, and they also have exams scheduled for Wednesday. So I may push it back to Friday. Just keep updated. Keep an eye out for what's going on. So just a heads up, that exam day may be pushed back to Friday. But I'll let you know later this week as we move through the materials, see what we can do. So yeah, let's continue today with equations of planes. So 12.5 continued. And last time we talked about the equations of planes. So last time we finished up with the equation of a plane, or we introduced the equation of a plane as something like a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. And for the plane, we had a normal vector, n, which was ABC, and then we had a point x0, y0, z0 that was just any point in the plane. And if we have a point in the plane and a normal vector, we can automatically know the equation of the plane. So that was the scalar equation of the plane. Now, today we're going to do some more examples. We're going to talk about distance from a point to a plane, and we'll be finished with this section. So first thing I want to do is look at an example here. And this actually combines the two concepts, kind of like we did last time. We found the intersection of a line with the plane, and this is going to be finding the intersection of two planes, which will be a straight line. So find the parametric equations for the line of intersection of the planes two x plus 5z equals -3, and the second plane is x minus 3y plus z equals -2. So these two planes are going to intersect, and I'll just try to graph that. Say I got one plane kind of like that, and I have another plane kind of like this. Then those two are going to intersect some straight line here. So I'm trying to find the equation of this line of intersection. So, and I'm going to find the parametric equations of that line of intersection. So to do that, we're going to, well, there's a couple approaches we could take. What I think I'll do is I'll use Gaussian elimination. So I have x minus 3y plus z equals -2. And then 2x plus 5z equals -3. And I'll use Gaussian elimination. So what I'll do is I'll multiply the first equation by 2 and then subtract the second equation. So that'll give me 0 here, and then that'll give me -6y, and then 2 minus 5 is -3z equals, this will be -4 plus 3, which is -1. And so I'll call this my new second equation. So this is the new second equation. So I've got two equations here, x minus 3y plus z equals -2, and -6y minus 3z equals -1. So at this point, I have two equations but three unknowns. And that means I have an underdetermined system because I have two equations, three unknowns. So what I can actually do is I can say one of my variables is free. So if I take this last equation and solve for y, we'll get y equals -1 plus 3z all over -6. So I can get y in terms of z, and then I can take that and plug it into the first equation and get x in terms of z. So it's like z could be a free variable. So z is a free variable. It's not determined. But once I know z, then I can know y and ultimately x in terms of z. So what we're going to do is we're going to say, okay, let z equal t and then solve for y and x in terms of z. So let z equal some parameter t, and that tells me y is going to be -1 plus 3t over -6, which of course I can write as -1/2 t plus 1 over 6. And then sub both of these into the first equation to get x in terms of t as well. But so far these are two of my parametric equations. And then sub these two into first equation. Whoops. And that will give us, let's see, x minus 3 times y, but y is -1/2 t plus 1 over 6. And plus z, which is just t, equals -2. And that was the first equation. I fixed that 3. Okay. Now I'll just distribute and solve for x. So that's going to give us x plus 3/2 times t minus 1/2 plus t equals -2. And simplifying that a little bit more, get x equals, let's see, -2 plus 1/2 minus t minus 3/2 t. And combining all this, we get x equals, let's see, -2 plus 1/2 is -3/2. And -1 minus 3/2 will be -5/2 times t. And so that is our parametric equation for x. So that would be a perfectly reasonable set of parametric equations because I let z be the parameter, basically. Since I had an underdetermined system, one of the variables, at least one of the variables, was free, and so I just chose z to be the free variable. I could have let y be the free variable and solve z and x in terms of y. But either way, it doesn't matter. So the intersection of two planes could be a straight line, just like this. It could be that the two planes don't intersect at all because they're parallel and they're separated. Or they could be the same plane, meaning they intersect everywhere. So then the plane of intersection would be the plane itself. So those are the three cases for planes. They could intersect at every point, i.e. they're the same plane. They could intersect along a straight line, just like this. Or they could not intersect at all because they're parallel and separated. Okay, cool. Questions? I'll just take a minute, see if there are any questions. Okay. Let's do a few more examples here, talk about a concept. The distance between planes, or actually the distance from a point to a plane. And we'll be done with this section. So 2 more examples and then a new concept and 1 more example after that. And we'll be done. So the next example says, determine if the planes are parallel, perpendicular, or neither. If neither, find the angle between them. So the planes could be parallel, perpendicular, or neither. And we have 2 planes here. The first plane is 2x minus 3y plus 4z equals 5. And the second plane is x plus 6y plus 4z equals 3. So solution, let's just draw two planes here. That would be parallel. If the planes were parallel, then their normal vectors would be parallel, i.e. they would either be in the exact same direction or opposite directions. So basically whatever the planes are going to do is determined by what the normal vectors do. So the angle between the planes would be the same as the angle between the normal vectors. So actually all we have to do is just compare normal vectors, and then the planes are always offset by 90 degrees from the normal vectors. So just look at each normal vector. So n1 from the first plane is the vector 2, -3, 4. We talked about that last time. If you know the plane equation, you automatically know the normal vector. It's just the coefficient of x, y, and z. N2 is 1, 6, 4. So there are our two normal vectors. And all we have to do is compare the two normal vectors. Are the two normal vectors parallel, perpendicular, or neither? So all I have to do is find the angle between them. So could do cosine of theta and just kind of skip everything, but let's look at n1 dot n2. So n1 dotted with n2 will be equal to 2 minus 18 plus 16, which is 0. Aha, their dot product is 0, so n1 dot n2 equals 0, so orthogonal vectors. That means the planes are perpendicular or orthogonal. So the planes are perpendicular to each other. Means there's 90 degrees between these two planes. So instead of the graph I drew for these two planes, the real picture is more like this. So they're actually orthogonal. So something like that. But to do this, all you have to do is look at the normal vectors of the planes. And to find the angle between the planes, we just have to look at the angle between the normal vectors, and it would be the same as the angle between the planes. It may ask you to find the acute angle between the planes, because there could be, let me just draw an example. Could have a plane that's kind of slanted compared to the flatter plane like this. And then there's like an obtuse angle here, then there's an acute angle over here. So it may ask you to find the acute angle between the planes, and then you would just do either cosine inverse of n1 dot n2 over magnitude n1 n2. So cosine theta equals n1 dot n2 over magnitude n1 magnitude n2. And if that's negative, your theta is going to be larger than 90. So then to get the acute angle, you have to do 180 minus that, or pi minus that, either way. Because you might have your normal vector like this, n1, and this one might be n2, And then in this case, theta would be greater than 90 if those are your normal vectors. But there's also an acute angle over here. So the blue angle is actually an acute angle. We'll call it theta C. Theta C would be 180 minus theta. So that's a possibility. You might have to find the acute angle between the planes. But in our example that we had, we know they're perpendicular, so we know the angle is 90 degrees between the planes. Any questions? Okay, next example. Says find parametric equations for the line through the point 510 that is perpendicular to the plane so perpendicular to the plane 2x minus y plus z equals 1. So this example says find the parametric equations for the line that goes through the point 510 that is perpendicular to the plane 2x minus y plus z equals 1. So let's think about this. We have a plane, some arbitrary plane like this, and we've got a point over here, 510. It's probably like not the right place to draw this, but we can always rotate it to make it work. So 510, and we want the line that goes through that point, so but perpendicular to the plane. Basically want the equation of this orange line here. So to solve this problem, we need to find the equation of a line. So to get the equation of a line, to find the equation of a line, we need a point on the line and a direction vector. Right, so to get a line, or a line equation, we always need a point on the line and a direction vector. We've got our point on the line, that's 510. Right, so 510 is our point that we're going to have on the line. So R0 is going to be the vector 510. But our direction vector for the line is just going to be the normal vector of the plane. So the direction vector of the line is going to be the normal vector of the plane. So our direction vector v, we used to call it, is just going to be 2, -1, 1. So we look back at our plane equation to get that normal vector. Once we have those, we can get our vector equation for the line, r of t equals 5, 1, 0 plus parameter t times vector 2, -1, 1. And so we get the parametric equations x equals 5 plus 2t, y equals 1 minus t, z equals t. T ranges from -infinity to infinity. And that's our solution. Any questions about that? All right, good to go. Let's keep going then. Let's move on to the distance from a point to a plane. So distance from a point to a plane. So we'll have a plane and we'll have a point. And the plane equation we'll say is ax plus by plus cz plus d equals 0. Just this linear equation of a plane. And we know that that plane has a normal vector. N, which is the vector ABC. And we'll call this point that's not on the plane, we'll call it x1, y1, z1. So x1, y1, z1. And we want to find the straight line distance right here from the point to the plane. Okay, so what we're going to do is develop a general formula for this problem. And we're going to use arbitrary variables x1, y1, z1, a, b, c, etc. So first thing we're going to do is we're going to pick an arbitrary point in the plane. Call it x0, y0, z0. x0, y0, z0. Let me draw it on the other side. So this point is the point x0, y0, z0. It's just arbitrary point in the plane. It's an arbitrary point in the plane. And now what we're going to do is we are going to create a vector that goes from x0, y0, z0 up to the point that's not in the plane. We'll call that vector p0, p1. p0, p1. So call it p0, p1. So the vector p0, p1, which goes from x0, y0, z0 to x1, y1, z1, is the vector x1 minus x0, y1 minus y0, and z1 minus z0. And now what we're going to do is project that onto the normal vector. So find the scalar projection of that vector onto the normal vector. So now find the scalar projection of p0, p1 vector onto the normal vector n. And that will be the length or the distance d. So if we project p0, p1 onto the normal vector, that formula is p0, p1 dotted with n over magnitude of n and we're going to take the absolute value just to get a positive distance. So dot product is going to be the vector x1 minus x0, y1 minus y0, z1 minus z0, dotted with ABC all over square root of a squared plus b squared plus c squared. And we work that out. That's going to be a times x1 minus x0 plus b times y1 minus y0 plus c times z1 minus z0 all over square root of a squared plus b squared plus c squared. And we're taking the absolute value of that. And so that's going to be a times x1 plus b times y1 plus c times z1 minus parentheses a times x1 x0 plus b times y0 plus c times z0 all over square root of a squared plus b squared plus c squared. But one thing to note is that since this point is in the plane, we can say that ax0 plus by0 plus cz0 plus d equals 0. So if I subtract these three to the right hand side, that's just a positive d. So I dropped my absolute value again. Whoops. So we can say that this is going to be equal to absolute value ax1 plus by1 plus cz1 plus d all over square root a squared plus b squared plus c squared. And that is the distance formula from a point x1, y1, z1 to a plane ax plus by plus cz plus d equals 0. Questions about that derivation? Okay. Let's look at an example that uses this formula. Now, I don't expect you to derive this formula every time. Of course, you can just try to remember the formula itself. Absolute value of a x1 plus by1 plus cz1 plus d over square root of a squared plus b squared plus c squared. But maybe a little complicated to remember. I'd hate to have to go through that derivation every time, though. So let's look at an example, assuming we remember the formula. So example, find the distance between the planes. So find the distance between the parallel planes. And the two planes are 10x plus 2y minus 2z equals 5, and 5x plus y minus c equals 1. So we can kind of see that the two planes are parallel. Just take the first normal vector, or sorry, the second normal vector and multiply it by 2 to get the first normal vector. So they are parallel. How do we find the distance between them? So solution. We've got two parallel planes here. I need to find the distance between them. So what I'm going to do is pick an arbitrary point in either plane. I'll take the second plane. Pick an arbitrary point in the second plane and then use the distance formula to the first plane. So pick an arbitrary point in the second plane, then find the distance from that point to the first plane. So probably what I want to do for that first plane is rewrite it as 10x plus 2y minus 2z minus 5 equals 0. So that'll tell me what my a, b, c, etc. are. So a, b, c, d when I plug it into my formula. All right, so how do I pick this arbitrary point in the first or in the bottom plane? Well, I can say, okay, let x equal 0 and z equal 0 in the second plane. Then y would have to be 1. And that would be a point in this plane. X equals 0, y equals 0, or y equals 1, z equals 0. So in that second plane, right, because our equation is 5x plus y minus z equals 1. So that would be a point in the plane 0, 1, 0. So that's our point 0, 1, 0. Now find the distance from that point to the plane 10x plus 2y minus 2z minus 5 equals 0. So now the distance d is going to be the absolute value of a x1 plus b y1 plus c z1 plus d all over square root of a squared plus b squared plus c squared. And that's going to be absolute value 10 times 0 plus 2 times 1 plus negative 2 times 0 minus 5 all over square root of 100 plus 4 plus 4. And that's going to reduce down to C0. So that's just 2 over square root of 108. Nope, sorry. 2 minus 5, right? Sorry. 2 minus 5 over square root of 108, which is negative 3 over square root of 108. And that can simplify to, oh, but we take the absolute value. So it's positive 3 over square root of 108, which is going to be 3 over 6 square roots of 3, which will be 1 over 2 square roots of 3. And that is the final answer. Questions about that? Okay, so could we use the 0.001? Well, let's see. It has to satisfy the plane equation right here. So 0, 0, and z would actually be -1. So that would be a 0.00. -1 would work. But if we used something 0, 0, we'd have to use 1/5 for x. So we have to satisfy this plane equation right here. So you just let two of the variables be 0, and then you determine what the third one should be to satisfy that equation. Does that make sense? All right, good. Okay, so I want to show you guys some more resources that I have for you. I got an email over the weekend. I didn't respond until this morning, but I think it would have helped to already know some of this stuff I'm about to tell you. So let me show you some stuff that I have available to you guys. Let's see, if we go to YouTube and we go to the channel, let's see. Oh, I can show you on my channel regardless. So let's see, Jonathan Walters. Let's see. I'll show you some things that I have here. I have a playlist of just random examples from different chapters of the Stewart Calculus textbooks. I have like a chapter 12, and a chapter 13, and a chapter 14, chapter 15. And those are nice playlists. I also have this Calculus 3 playlist, which just has like all the examples in one playlist. Whoops. Don't necessarily want to look at all of them individually like this. So in this video, we're going to pause that, sorry. View full playlist, there we go. And it has a bunch of examples. You could say, are the two vectors parallel? Find the magnitude and the angle of the resultant force, find the tension in the cables, dot product of two vectors, how to find the angle between two vectors, find a unit vector perpendicular to two vectors. This was one that was I got an email about. Find the force needed to supply 100 Newton meters of torque, and that's actually the example that I referenced in that torque video or that cross product video. Acute angle between a line and a plane. That's a difficult example that I just threw in. It's not actually in the textbook or anything like that I know of, but I just threw that in as an extra example. It's a really good one. It's kind of tough conceptually, just to make sure you get the acute angle. Angle between intersecting lines. First, show that they intersect, so that would be good. Are the planes parallel, orthogonal, or neither? Find the angle between the planes. Yeah, so just a lot of good stuff there. There's tons of examples for all of the stuff that we're going to cover in this course. So it's just extra examples that students are always asking. They're always like, I want to see more examples. So it's kind of why I started this whole YouTube channel thing. So you guys just check out those examples. If sometimes I have the exact problems from the homework in there. Sometimes it's just arbitrary problems that I made up, kind of like this problem here, the acute angle between a line and a plane. I really like that problem just because it's so conceptually rich. So this one is actually similar to a problem in the homework, but it's actually a little more complicated. So just find the tensions in the tension in the cables. So just a bunch of good examples here that are not in the playlist I provided you in our course. So you can just kind of snoop around, see what you can find. I also have them split up by chapter, like I said here. So if you just want to look at a specific chapter like this one, it's all the same videos. It's just chapter 12 examples. So it's up to you. And if you know in the future you want to look back and you're in a different course or whatever, I have differential equations lectures, I have differential equations examples. So just whatever. You don't have to use any of this if you don't want to. Just throwing it out there. Just letting you know it's there. So anyway, cool. Any questions? I think we'll just call it a day. We've only got like, I guess 15-20 more minutes. I'll just see if anybody has any questions about homework and stuff like that, and if not, you're free to go, and we'll meet back on Wednesday to go through some conic section stuff and get prepared for three-dimensional surfaces. So cool. Yeah, if no questions, I'll see you guys later. If you have a question, just hang out, ask on the chat. I'll try to help you out.